All right, welcome back. And today we're going to talk about project number 1. So today, a summary of the last session was threads, concurrent programming. We went over what is concurrent programming and why the threads are defined the way they are, why we need them. Threads and processes and the differences between having multiple threads or having multiple processes. Threading examples and threading pools. There are a couple of examples which were like for web servers and editor, and what a thread pool is and why we need them or why we use them. What are the benefits of using one? Implementation and multi-threading models within the kernel, user space, many-to-one, one-to-many, one-to-one, and some issues that we covered in the processes, and then now when we have like multiple threads, how is a fork or exec implemented? What's how a thread gets canceled by another thread within the same process, and so on, right? So today I'm going to first check that you have familiarized yourself with the code in the Pintos, and that you have gone over chapter 1 and 2 of the manual, as well as the reference guide parts and the coding standards and project documentation, which is going to help you a lot when you are in a group working in a group. All right. So then make sure that your groups are set and you can clone your repo. This week or by the end of the weekend, we will add you to AutoLab AutoGrader. Who has worked with them in another course? Just raise your arm. Okay, yeah, okay, that's good. So it's pretty useful. So starting from last fall, we started using it for CS 421, and so that way, when you submit, you make sure that what you get is what we get. The same score, same results, and if not, you can act accordingly and not having like environment issues and everything. And so we put the instructions for assigning your groups there, as well as your initial submission. All right? Any questions? All right. So today we're going to talk about our Pintos project number 1, threads. And so there are different parts into this. So a Pintos, fully implemented Pintos, is a whole operating system that has a boot support, device drivers, and a memory manager, and a basic file system, threading simple scheduler. These are already there, and once you have it fully developed, then it is expected to have a priority scheduler, alarm clock, multi-level feedback queue scheduler, page fault handling, address space manager, page replacement, and the multi-threaded file system, and the rest of the system. And there are 2 also components for testing it, which again we might talk about it a bit today and in your recitations. So in order to test the kernel itself, there are some kernel mode test cases which are specific into the kernel, because from a user space there are certain things that you cannot test within a kernel. So these are what you're going to deal with in your project 1. And there are also some tests in the user space that test the functionality of your kernel, as expected by a user program. And so these are part of the Pintos code. Now, you have been given this. Right now, this is what it is in the repo. And you are going to take whatever is there and understand. Well, you don't have to understand all the device drivers, obviously, but you're going to cover what you need to understand to then implement this part, which is the alarm clock, priority scheduler, and priority inheritance, and multi-level feedback queue scheduler, right? So this is your task for project 1. Now, this has multiple steps. There are 5 steps. One is preparing yourself, which if you have followed with the assignments and reading assignments and reading the manuals, you have partially covered this. But after that, you're going to make sure that your Pintos is set up. Hopefully, again, we try to initiate all the environment setup, all the TA help earlier on during the semester. So hopefully, everyone is now set up with their Pintos. And there are a couple of things that you need to check just to make sure it is actually set up. If you basically run the VM, it should be set up. I mean, either it doesn't run or freeze or something, or it runs. And then you gotta like start getting started with your design document, which we're gonna talk about today. That is more important. I'm not gonna say that it's more important than the code itself, obviously, but it would be much more important than a normal, design document for a different project that you might have done in other courses. The more time and effort you put into this, it will be easier for your implementation, which is your next step. And then after that, obviously, you need testing. So you're going to like spend a lot of your time in these two steps: implement and test, implement and test, implement and test, and implement and test until you give up, right? So for preparation, there are things that you need to do. The first thing is to read chapters 3, 4, 5, 6 from your textbook, and those are the processes, threads, CPU scheduling, and synchronization. So we have covered processes and threads in the lectures. In the next couple of weeks, we're going to cover synchronization and CPU scheduling. Today, you might hear a couple of jargons, but don't worry about them. We're going to cover them in depth, but it's just like what you need to know about Project-1. And or at least you got to like make sure you will understand in the next couple of weeks what you need to know. And then definitely cover the rest of the Pintos manual, introduction, Project-1. This gives you a lot of information of what the Pintos code and what the files and the directories are. Appendix A reference guide 1, 2, 3, 4. Again, these are all important. If you again take it at a slow pace, each chapter is a few pages. It's not that you should sit down and read the whole manual. No, but then once you skim through them, then you need to know where to refer, when you're implementing. And then Appendix B is 4.4 BSD scheduler. You don't need to read it now until we actually cover it in the lecture, but this is something that you need for your implementation. And then coding standards and project documentation. Again, hopefully you might have skimmed through it within the last couple of weeks. All right. So then you have to make sure your Pintos is set up. So you got to use the VM, and then just go ahead and open a terminal, cd Pintos directory and source threads, and then do a make. If your make process finishes successfully with no error, basically, that's how you do it. You run your make command within the threads, right? This is a complex code. There are many make files in there, So you're gonna in your Project-1 when you want to compile, you got to be in the threads directory, and then you can obviously make clean and then remake. And then there are make tests and make check and make grade. So these are all things. But if you just want to compile your code, any other make check or make grade, it will make it longer. So just a simple make in the threads directory is what you need. And then how to test it? You go to to the build directory within this directory. You go to the build, and then you run. This is one of the kernel tests basically. All right, when you run Pintos run, then it basically runs the alarmed single. This is one of the tests. You can also go to make check or make grade. That will basically run all the tests on it and then gives you a whole result. But when you were focusing on to fix one test to implement, for example, the alarm clock, well, you don't need to test your MLFQS, which takes time, or your priority scheduler. You only want to make sure that one task is getting done. So this comes handy. So then this is, if you run Pintos run alarm single, if you run a single test by yourself, then the box or QEMU will run, and then basically this like boots your Pintos into that virtual the emulator basically within your virtual image. And then basically the boot complete, you see the message here, that means the kernel is booted. And then executing alarm single, this is what you have passed on to the kernel as an argument, right? So the kernel starts running this test within itself, and then it basically gives you the output of the test, and then at the end it says like execution of alarm single complete. And then, so this just shows that, how a test is run. Now, you might find these, information useful if you are, again, running a specific, you're modifying a piece of code and you want to make sure that this test gets run. All right? So you can just do it now, right? You can run the other test. Either it fails or passes. It doesn't matter, but it still should run. So then you got to like familiarize yourself with the code. So again, I'm going to ask for a couple of complex projects that you think you've done in the, in your last 4 years of here. Just give me a couple of examples. I really want to have a reference. Class projects, go ahead, raise your arm. Let me know you've implemented something in the system. Yeah, go ahead. Why do you laugh? Go ahead. Nothing yet? You're either juniors or seniors. What have you done? What the school does? Seriously, go ahead. What have you implemented? What is if you want to like go into an interview and they ask like what is the biggest code that you've like implemented or hard? Yeah.
Me? What was his answer? I think he doesn't know.
Yeah.
I remember in 321 implementing. I don't remember what we implemented, but it had to do with. So I remember, but I don't remember. It had to do with like.
Was it a group project?
What's that?
Was it a group project?
Yeah.
Okay.
Oh, it was Xenu.
No, I'm just kidding. So does anyone know what was that project?
Xenu?
What is that?
It was like nobody had that? Was it Dina? No? Okay, never mind.
Okay, you give me an example. Go ahead, come on.
Nothing very common.
It's being recorded.
I don't think after any class it has like an extensive code base that I've worked on. It's really good. Like a lot of it is just like making like a web app or
Web app, okay.
working on assignments where you really have it. It's a smaller assignment, nothing related to like this scale. I can't pinpoint anything.
Okay, good.
IoT dog collar.
IoT what?
Dog collar.
What's that?
Internet of Things and like a dog.
Oh, okay. Good. Okay, that's a piece of program which is, but in most of the cases, what you implement is, first of all, you implement most of it, right? So you know what you're doing, or at least you have an idea what you're going to do, right? And that's and then most of it is they have like a single scope, right? Either you implement like a one file, or a class and a couple of files besides it, or a couple of directories maybe here and there to organize itself, but basically. But this is just like it's an operating system. You have to realize that, and it has a lot of code. So what you are implementing is not huge. Maybe in project number 1, what is it, like 400 something lines? It's 400 something lines of code. It's not big, but in order to understand what you need to implement and what to modify, that takes a lot of code reading from the Pintos itself to understand what's going on there. And then, how, because it is already there. You can't just implement something, wherever you want, right? It has to adapt to the rest of the system. And so there are things that are already there, again, threads and synchronization primitives. There are lists, there are tools, and that you have to use. Otherwise, it would be too difficult. If you want to start from scratch, there are not a lot of like C or C++ tools that you might use. There's no vector or anything. If you want to start from scratch and then build a linked list, then you will just wasting a lot more time. Unless you actually understand that, hey, there is a list implemented in the Pintos libs, and then I have to go and read how it works, and then actually utilize that, and it makes my life much easier, right? And again, you don't have many tools because you're working, at a very low level. So you got to use whatever you have. It's like a zombie apocalypse. And then make sure you go over the source files of the manual just to see what are the files within the threads. And we might just take a look at a couple of them today, but you should definitely go read. Try to follow the code. Again, the sequential code is not really clear, right? Because it has interrupts, it has events, and then basically you should it would be difficult for you to understand where the flow of the code is, but you need to understand that. All right, so the threading system implemented in the Pintos is in thread.cnh, and the sync.cnh also are for synchronization primitives, right? You have to understand everything within these two C files and header files, right? It will take you quite a bit of a time, but again, if not, that makes it difficult. So Within these, you understand how the switching between threads actually happen, or how a context switch is called, or what is the code for it. There is a piece of code that you technically don't need to understand, and that is sketch.s. This is assembly code, which is getting called within this within the schedule function. But basically, you already can tell that's basically when a context switch happens. It's good to understand, but it's not essential for you to read that assembly code, basically. And then the scheduler is implemented in this file, and also the synchronization primitives, which are semaphores, locks. We're going to cover them in the next couple of lectures. But basically, we have already talked about the issues when you have multiple programs running. They have to communicate with each other, not to access a shared variable at the same time. All right. So then the important directories for your Project-1 is the threads, which again, it's most of the base kernel code itself is in here. The devices, which have the device drivers, most of them you don't have to care, but because you want to implement alarm clock, you need the timer, right? And if you remember, the timer is a different device. It's actually in your computers, it's a separate chip that gets configured, and then it keeps track of time, and it interrupts the CPU when a tick happens. It's called a tick. With a certain amount of time happens, then it just lets the CPU know, so the operating system can either context switch or count the number of times or amount of time a process is running. So that is what you need. In lib kernel is C libraries that you need. So understand this lib kernel tools here, and these are definitely useful for you. So the list is one of the important ones. The list is we're going to actually cover the list. Okay, here it is. You're putting a lot of effort in it. All right. Tests is basically the test that we showed in the Pintos picture, right? So your kernel is part of the kernel is testing itself, and some of it is also running the tests. So these pieces of code are there. You can basically read them just to see how these tests are actually running and what are they doing. And you can modify them if you want to print out something extra, or skip some piece of test just to make sure you reach the second step or whatever. So this is for you to play with, and then your result also might change. So just know that whenever you want to actually grade your code, make sure you check out the original ones. This is also what happens when you submit. These will be replaced with the original files. Okay. Any questions so far? Okay. So these are, again, the important files. The threads.c and h are the thread support. So most of your lines of code should be will probably be in these. And then sync is, again, synchronization. You might edit some of these. For example, when you want to implement priority in your locks, you have to modify the locks. Or even in alarm clock for semaphore or locks, you have to put pieces of code in these. And then in the timer.c and timer.h, you need to modify the timer interrupt handler and timer tick, I suppose. There are not too many functions in this that you need to modify. I think either 2 functions. But just to know that this is the place. And list.c and h is something that you should definitely read. A lot of these header files, I'm not sure even in C files, there are a lot of comments. There's like pages of comments within the file just to show you what are the data structures used in here, what are the thoughts behind them, and how to use them. And those are very useful. One specifically is list, because this is not very intuitive. The way that you understand a list works normally, I guess in C++ or Python or whatever, is that you have a list of data structure that you can just directly access, right? Like you define an integer of 200 and then variables, and then you just access them with the bracket. Well, this list is not like that. It's a linked list. I'm not sure if it was I think it's a double linked list. But it's not also a linked list like a normal linked list. Who has written a normal linked list here? Just raise your arm. At least I know how many people have an idea. Okay. So you already know what a linked list is. But your linked list, again, is basically a list of pointers that point to your data structure, right? So you have a linked list of integers. So it gives you basically a data structure that points to each other, but each of them contains an integer or points to another integer. Now, in this list is different. You have to probably go to recitation. We don't have time to go over all the details. But there is an lm, which is a part of a bigger structure. Now, this lm can be part of any struct. So it can be a thread struct. It can be a lock struct. It can be, whatever struct. All of them use this lm, and the list is just the list of lms, these elements, basically. And then there are a couple of macros that allow you to basically retrieve the main data structure. So that allows you to have one type of list, not like an integer double linked list, not a floating double linked list. It's just list. But it can basically be used for any type of data structure. All right? So make sure you understand it. And then this is also how the kernel gets initialized and basically starts booting. So if you want to know, okay, where does it start? Is it in where is the main.c, whatever. So this is the place that you probably should start, right? This is the data structure of the thread itself. So we have each thread contains a TID, which is the thread ID. This is the identifier of the thread, unique number. And there is the status of the thread, which is going to define if it's a running thread, if it's blocked or ready, whatever. This is the status. And then there's name, 16 bytes only. And then there's the stack pointer for the kernel thread within the basically it is within the thread allocated space. It's in one page. We're going to show it in the next slide. So the priority of the thread, which you're going to definitely use in your priority scheduler, MLFQS probably, then the list lm that I just mentioned. So this all lm is used only in the list of all threads, right? And then there is another list lm. It's called lm. This can be used in different lists. You can move this is a hint basically that when you move an element from one list to another list, if you move one element from one list to another list, then so this thread struct has one element, right? This only has this, and then this element can be a part of list 1 or list 2. And within the list, you are only working with these elements. You're not working with the thread struct. You're just moving these elements back and forth, moving through the the double linked list. And then if you take that element from this list and then link the other two previous and the next together, and then put this element in another list, now what you have done is basically kind of move this thread from this list to this list. So by basically moving the element between the lists, you can just define if this thread is within this list or this list. Now, where you want to use that? When a thread changes its status from ready to waiting, right? One thread cannot have the same status at the same time. It cannot be in the ready state and waiting state at the same time, right? And this gives you an idea that they are basically mutually exclusive, meaning if a thread is in the running state, then it should be in the running queue, like a list. When it wants to change its status to blocked or wait, whatever it's going to wait on, you should move it from the ready list and dump it into that list. That's as simple as that, right? So this piece, you don't have to worry about it. It's going to be used only in your project 2. And then the magic number, this is just a number that gets replaced when the stack overflow happens in your kernel, and then basically kernel can tell and then crash. So this is a page or 4 kilobytes of space allocated to each thread structure in your kernel memory. And so start from wherever this thread struct is allocated in the memory space, you have this TID status and all that first. and then all the way to the magic number. So whatever the kernel wants to do, in a lot of cases, it first immediately checks this magic number. If it is not touched, it's basically just a a constant number. I don't remember what is it. It's just like a constant number. So if this byte is not changed, then everything is at least as expected. But if this byte is not as expected, it's not the same constant as as defined. That means that the kernel stack has grown so much that has overwritten this part, and that's a failure because now your TID status, all of these might be just garbage, right? So that thread struct is not useful anymore, and then your kernel crashes, right? So if that something happens, if you during your implementation, I don't actually think this might happen in your project 1. Any of the projects, if something happens and then there is an assertion that shows a magic number assertion error or something, and you're like, what have I done? I haven't touched this. This is the reason. Your stack has overgrown. You have defined a lot of local variables. You have made so many calls within your kernel code that your stack has grown so much. And all right. So the step 3 after understanding all of that is basically sit down together with your group mates, think through what you're going to do, what is needed, what is your approach, what is to be fixed, where you think that you have to implement and modify to implement the functionality. We're going to talk about it in the next, but you have to first sit down and do the design document. So the design document is a very simple text file. It's in the document folder in your Pintos directory, and it has like 4 files. Threads template, user prog template, VM template, and file system template. For project number 1, you're going to take threads template, rename or copy it first, copy it to thread.txt, and then just start modifying that, right? And this is what you're going to submit for your design document, threads.txt, okay? And we're going to show it, but leave a lot of it as is. You don't have to worry about, make it neat, whatever. So this is the text file. So first of all, again, it has like CS140, Project-1 threads. Leave it as is. In the autograder, we might just look for something here just to make sure that you have not submitted the wrong text file. Just leave it as is, but you replace your group names, group mates names and emails. Just replace this. And then the rest actually starts here. So the design document has some questions so that you can tell. If you can answer these questions confidently, that means that you have thought it through, or at least have an idea of what you're going to do, right? So for example, for an alarm clock piece, it goes like, copy here the declaration of each new or change struct or member, global or static variable, type def enumeration, right? So in this thread struct, you're probably going to define a lot of things. You're going to define variables like integers, or you might even define structs here. You might define a separate struct somewhere else, right? All of these, you are allowed to do that, but first of all, this gives you an idea that some of these questions might give you an idea. Have you thought about this issue or not? And then if you think about it through and then have an idea, try to make sure that it's consistent with the rest of the ideas that you have, and then answer these right below. You don't have to replace or remove anything. Just write down right here in a text editor. Nothing fancy. No document like Word. Nothing. No PDFs. Just here. All right. So again, how are race conditions avoided when multiple threads call timer sleep simultaneously? Okay. So this gives you an idea. Oh, have I thought about this or not, and how to approach it. And make sure you have detailed answer for these, right? So if you say, how are race conditions avoided? Using synchronization primitives. Well, okay. But that's not going to help you in your code, right? The same thing is not going to help you with probably your grade of the design doc, right? So the more detailed you think and answer your design doc, that's basically paving your, way for your implementation, all right? So don't give short answers or just very obvious answers. How are race conditions avoided when a timer interrupt occurs during a call to timer sleep? Again, just don't say with the lock or semaphore. just have it defined. Okay, I have defined this variable. This is for this purpose. In this function, this function turns it on. This function releases the lock. Think of it through. Now the implementation. All right. Before going through these steps, any questions? All right, so the implementation has 4 steps. If you look at the manual, actually the priority scheduling and the donation are within the same part in that same section in your manual, but basically they should be approached separately. So the alarm clock is an alarm clock, like the idea of an alarm clock, right? So you set it, you go to sleep, it wakes you up, right? That is exactly what's going to happen within your kernel. Within the kernel, a process might want to sleep. It just like doesn't want to get the processor. Why? Because it doesn't have anything to do, right? So if the processor, if the OS assigns the processor to this process, just a note here, we use process and thread interchangeably in Pintos because they are basically, each process and thread is basically almost the same thing. So just remember that when we talk in Pintos terms, when we talk about process and threads, they're the same thing. Okay, because we don't have multiple threads. If a thread wants to wait for something, if the OS schedules it, it says, okay, is that ready? Oh no, okay, I'm just going to yield back again for another process. If another one comes, and then again OS schedules this and asks, okay, is it ready? Oh no, okay, I'm just going to go back, right? And this is just doing nothing except killing CPU time, right? So instead, an alarm clock is a tool that it gives a thread. The thread tells the OS, wake me up within 1 second, or later on, the alarm clock specifically deals with the time. So it asks, wake me up within 1 second, and then it goes to sleep. It does not get any processor time until the OS decides that, okay, now it's the time, and then brings it back to ready list so it can get scheduled, right? Otherwise, again, it's just like, whenever it gets scheduled, it checks the time. Okay, what's the time? Is it time? No, go back to, the queue. So this is the first step. Then you gotta implement priority scheduling. Priority scheduling is when different threads are running at the same time, meaning one after another, or they're all in a queue. Now, there are multiple ways that they can get scheduled. We're going to talk about it in the scheduling in the next couple of sessions. But priority gives them a higher or lower priority. So as long as a higher priority thread is running, there is no CPU allocated to a lower priority thread, right? And then this is something that you need to implement. And then the donation of a priority from a higher thread to a lower thread. And after that, the multi-level feedback queue scheduler, or MLFQS. You see this quite a bit. And this is a very complex, relative to the other ones, scheduler that you need to implement. This is kind of independent of these because your Pintos runs either on the priority scheduler or on the MLFQS. This is like given as an argument. So, it's one or another. So the implementation can be somewhat independent. All right? So starting with the alarm clock, you have to re-implement a timer sleep function. So if any thread wants to sleep for some amount of time, they will call this function. Now this function is within the kernel, and right now it is defined as this. So when you call this function, the thread basically, after checking the assertion and so that the interrupts are on and everything, it just enters a loop and then yields. It yields and yields and yields and yields forever and ever and ever until it has elapsed enough time that it wanted. Again, it just keeps checking the time. If not, just goes back into the queue. This yield puts it back to the queue, allows another thread to get scheduled, right? Again, checks and again checks and again checks. And this is something that you don't. Instead of these 2 lines, you have to implement the alarm clock. How? You remove the thread from the ready list so the operating system does not schedule this, and instead put it back after sufficient ticks has elapsed. You remember that I talked when you take a thread from one list to another list. Now that list, the operating system should know at which intervals, check that list, who has to be woken up, and then bring them back to ready list. This is what you need to do. Okay? So any implementation of your code that uses busy waiting, which is this, which is the thread is technically waiting. It's not doing any process, but is keeping the CPU busy, right? So this is called busy waiting. Any of the implementation that uses this will lose the points, right? Next task is your priority scheduler. So in the ready thread with highest priority gets the processor. Again, you have multiple threads. If you implement priority scheduler, then the higher priority threads have the dibs on the CPU basically. When a thread is added to the ready list that has a higher priority than the current rerunning thread, immediately yield the processor to a new thread. So if a thread now wants to create a separate thread, right, we are allowed to do that, all right? Now this thread is running on a low priority, and now a new created thread is of higher priority, right? Now this is called preemption. So you have to stop the current thread and then start the higher priority. So this is another part of your implementation. When threads are blocked and waiting on a block, for example, maybe on a clock in your alarm clock, maybe they're waiting for a lock or semaphore, whatever. If it is time to wake a thread or multiple threads, then the one with the highest priority should be woken up first. And compare the priority of the thread being added to the list with that of running. Again, this is part of, you have to understand where these things are happening, right? So if you want to preempt a thread with a new thread, right? A new thread is added, and now you have to stop the currently running thread and schedule the other one. When is this happening? Think of it, when is this happening? When a new thread is getting created. So, it has to do with either create thread or thread create, and then understand what's happening there and where you should stop the currently running thread. And then select next thread to run based on priority. So whenever that a thread it wants to get scheduled, you have to take a look at how is it happening. Right now it does not treat any other thread with their priority. That's what you need to modify. Now whenever a next thread wants to get scheduled or chosen, then I have to choose the one with the highest priority. This is again what you need to look for. Compare priorities of waiting threads when releasing locks and semaphore and conditions. Again, when multiple threads are waiting for a condition, that condition can be a condition variable, a lock release, a semaphore up, and at these times, again, you gotta check, okay, I should not just pick the next one, I should pick the best one, the highest priority. All right, any questions? All right. So implement priority scheduler, the rest of it. So in thread yield, you have to probably use it, because thread yield is when a thread calls this function. It tells the operating system, right, force me out, right? Just schedule me out and schedule another thread and replace me, right? And the reason is, again, this is a piece of code of basically the kernel thread. These are all running in the OS, right? This is not a piece of code that a user space can run. Remember that, right? But when a user space call a system call, for example, if it wants to, now that it wants to sleep for some time, it then transfers the control to the operating system. So it's still running the same thread, but in the operating system mode, with within the operating system code that you are now writing. And so now you can call different functions within the kernel. So think of it this way. When a user program asks the operating system that I want to sleep for a couple of seconds, what's happening? Within the same process, it transfers the control to the operating system. The operating system checks and uses the same allocated space for this thread, and then stores the information that it needed, how long you want to go to sleep, which timer you're using, if you want to wait for a lock, then which lock are you trying to access. So then these are all basically put in the same allocated space. And then there are within the kernel now there are different functions. This function will allow this thread to be scheduled out and then force another thread schedule in. So when you call this function, the currently running thread goes back to the ready list, and then the scheduler is invoked and picks a new ready thread from ready list. Then in this case, there are multiple cases. So when you schedule in and out in your priority, if there is only one thread in the queue, then the scheduler puts it back in the queue and then comes and then wants to choose another one from the queue. This is a single one again, just picks it, put it back. It just gets rescheduled, right? But if there are multiple threads, then now if you, right now, if just like one after another, it's like a queue of threads, whatever that goes scheduled out, it goes to the end of the list. Then the scheduler takes one from the head of the list and then gets it scheduled. Again, once it's done, goes to the end of the list and then back in. But if you now implement the priority, the scheduler should not just take the first one in the list. It should go into the list or pick the best one, right? Which has the highest priority. And then if a different thread has the if different threads have the same priority, then they should kind of go into a first in first come, first in first out in the same queue. Within the same priority, they have to have the queue. And then if the other threads have the lower priority, again, the same thread should get scheduled, right? So even though it was put in maybe the back of the list, or that's how you want to handle your list, but even though it was just scheduled out, again, if it's a highest priority, it should get scheduled back in, right? So this is the diagram for this. So from running to blocked and ready, these are the states of your thread. So when a thread is running and it calls a wait, for example, it wants to acquire a lock and that lock is not available. So basically the thread does not do anything until that lock is released, right? So it should go and get blocked and wait for that. So in this case, it should wait for that event. When that event happens, so when another thread releases that lock, your operating system should basically watch out. Okay, who was waiting for this lock? You have to have a way to keep these things. And then when it is a turn for a thread to basically wake up, then you put it back to ready list. And then between ready list and running, the scheduler keeps changing. From the ready list, the scheduler picks a process. When it's time, when for example another thread comes with a higher priority, or it's just like a time quantum is over and it's it's turn for the next thread, your kernel should preempt it and put it from running to your ready list. All right. So in your priority scheduler, for example, you have to re-implement the next thread to run function. This basically is a function that you have to go over your available threads and then pick the next one, which is its turn, so that then the scheduled context switch can happen. So you have to implement it to implement the priority. All right. So now we're going to talk about an example of priority inversion. When you implement priority, there is a interesting glitch that can happen. So a priority is when a higher priority thread basically takes over a lower priority thread, right? So as long as there's a thread running with higher priority, a lower priority cannot run, right? Now, an example that this might not be happening is, for example, when you have a thread that is like of high priority and you have a lower priority thread, and now for some reason because this is not running, this is not making progress, right? But at some point maybe the higher priority thread wants to wait for something or a task which is done by this, right? So if your higher priority thread wants to wait for this, then obviously this has to get scheduled. How it happens? Because then this thread is not in running state anymore. This goes into waiting state, and then now this thread should finish its job, so that the lock is released, for example, and the event has now happened, and now the higher priority comes back to the ready list and then makes progress. Now there is a glitch that can happen. This case is simple and with no problem. But if you have 3 priorities. If we have many priorities, but this is an example. If we have a thread with low priority, a thread with medium priority, and a thread with higher priority, right? Now, if a higher priority thread wants to wait for the lower priority thread, we just made an example, right? The higher priority just goes away, then the lower priority runs until it makes the communication, gets the data ready, releases the lock, whatever, and then the higher priority is woken up, that was waiting for this, right? Now, what happens if the higher priority goes away, but there is also a medium priority here between these that was not running when this was running, when the higher priority was there, but now that the higher priority thread is gone, the medium thread, medium priority thread takes over the lower priority, right? So now the medium priority thread keeps running, and takes the CPU, does not allow anything of the CPU time to be allocated to the lower priority. So what has happened? There is an actual higher priority thread waiting for something to happen. So basically that thing to happen is important. That thing is also of higher priority, right? But now it's not running because another thread is running in medium priority and then it does not allow that to happen. So this is an actual case in the Pathfinder rover on Mars, right? So apparently, there was an issue with different threads. So the case that happened, I think the medium priority thread was some kind of communication which took long, and the lower priority thread was something that was relatively short, but at some times the higher priority thread needed that information, right? But every now and often when the higher priority thread was waiting for the lower one, the communication would happen, and it was like a long communication, right? So it would not allow the higher priority to come back, because it was waiting on a low priority which was not making any progress, right? So basically this can actually starve your higher priority thread. This can lead to a starvation of this. In the case of this rover, every now and often a watchdog timer would realize that, okay, why this higher priority thread is not running for a long time? There is something wrong going on, and your code in rovers billions of kilometers away, they have to be robust, right? There's no one to push the reset there, right, or fix something. So they rely on these things. So every now and often they would just restart the whole system, and thinking that it has crashed. So this here requires priority donation. When a higher priority wants to wait for low priority, that specific job that this thread is waiting for is also very important. For that amount of time, within that duration, this low priority should be bumped up to high priority, the same priority as this one, right? So when a higher priority wants to wait for a lower priority and make sure that this one makes progress, this donates its own priority to the lower thread. This bumps up. Now a medium priority cannot intervene this one until it releases that lock, and then it goes back to the lower level. Now the higher thread is not waiting anymore. Now it can get scheduled back, right? So this is something that you need to implement. Now, for implementation, remember to return the lower priority to previous priority once it releases the lock. If you don't, then you have bumped it up and you left it there. It was originally a lower priority thread, but now you've bumped it up to a high priority. That's what you don't want. Be sure to handle multiple donations, right? If there are 10 levels of priorities, and then all of these wants to wait for this lower priority, when you have to remember that then the highest should be donated to this, right? This is something that we have multiple. And also there is nested donations. If H wants to wait on M, M wants to wait on L, and so on, the donation should basically propagate all the way, right? So this you should think about thoroughly, because what happens when the lock is released? Should I go back to medium? Should I go back to high? Should I go back to low? How do I remember what was my previous level and then my previous levels? Okay, so these are things to remember when you design. And this is they have put up to 8 nested, meaning a thread waiting on another thread, waiting on another thread, another thread, another thread. This now has 8 levels. So if you are planning on a queue or array, whatever list, this just gives you an idea of how long that should be. All right. Now synchronization. any synchronization can be easily solved by turning interrupts off. Why? Because you're running only a single thread at a time, and a thread won't get scheduled out or intervened if the interrupts are off. Remember, timer is also an interrupt. If a time passes by and this tick, that timer tells the OS that this time has passed, so take this thread, put it away, that is an interrupt. Now, if you turn off the interrupt, meaning you're wearing headphones on the CPU, and the CPU is like working on this thread all the time, ignoring all the timer interrupts, ignoring all the inputs, right? Basically, then there is no race conditions. There is no way that two threads have, race condition to access, something. That only happens when interrupts are on. So, I have this piece here, I am modifying this, and then a timer happens. I'm just like frozen here. My operating system just moves me away. And then it schedules another thread. That thread also wants to use this, and then they start modifying this, right? And then now we are basically thinking that I'm modifying this while I was frozen. Another thread modified this. This is the case of a race condition, right? And this is why the synchronization methods are used. So again, let me tell you an example. Okay, I'm just going to use this, right? So a lock, for example, is to give an owner to this, right? So if this can be written only with this specific pen, now if I acquire this pen and I'm writing and I'm frozen, I'm put away. If another thread wants to write here, he's looking for this, right? I need this to write. I can't. So I have to wait for that thread to finish before I can modify this. So the other thread goes away, and until I release this, no one else can write it on this. This way, we cannot modify its shared variable at the same time. This is a job for a lock, right? Now, again, as I said, this only happens when you have multiple threads getting intervened and preempted. But you should not do that. You should not turn interrupts off, because that's not the way to do it. You don't want your operating system just to, ignore interrupts. That's wrong. What if a thread turns the interrupt off and crashes, right? So any implementation turning the interrupts off for synchronization purposes that can be done with, locks, semaphores, and all the other things, it will be points will be taken off from it, right? Yes. We will talk about them in the next week's lectures. So they are all synchronization primitives. They're used in different methods depending on the functionality, right? A lock is simply to understand, as I just mentioned. A semaphore is actually how a lock is implemented. It's more general. It can have, instead of just acquiring and releasing a single Boolean value, it can have an integer value with numbers, basically. When you have multiple markers available, for example, how you can associate multiple markers. Again, the examples will make it clear, right? But again, you'll understand what are they and how to use them. And then just remember, you have to use those primitives instead of turning interrupts off. All right? So next, the only place, okay, I forgot this. The only place that you are allowed to turn interrupts off is when you are handling a synchronization between a kernel thread and interrupt handler. Because interrupt handlers cannot acquire a lock or something because they cannot wait. Interrupt handlers should be very short and quickly, give the process back to the main thread. So within the interrupt handlers, you cannot acquire a lock or wait or down a sema. So in those cases, basically, you may use this, but that should be only one or two places. You remember? Yeah. So your codes will be basically revised later. If you're using interrupts off for any other purpose like that, then it will lose some points. All right. After implementing priority and priority donation, now it's time for advanced scheduler. Right. We're going to talk about the details of this scheduler in the scheduling lectures, but just remember that this is the scheduling is not as simple as either priority or first come first serve. There are multiple scheduling schemes. Some of them have feedback. Some of them have multi-levels. So for example, in your Pintos there is this Boolean value thread MLFQS, which tells you in the line I think 60 of your thread.c that if this is this is set true or false by the init. So you don't have to worry about setting it, but you should use it in your code. If it is true, then your scheduler should basically schedule based on the advanced scheduler. If it's false, then you should just, or by default it's usually false for all other tests and your priority alarm clock and all, then your scheduler should just be your priority scheduler. So when you have multiple queues, it's like this, right? So maybe you have different queues based on the category, right? So system processes, interactive processes, and student processes, whatever. And now you might have different priorities for each of them. So that you don't compare a student process with a system process. You don't compare these. If there are multiple system processes, they get to scheduled based on one scheme or algorithm. And then if it's a turn for a student process, there is another algorithm or scheme that tells you, okay, which student process should be scheduled, right? But you never replace a student process turn with a system, right? This is when you have like multiple levels. Now, what is a feedback queue? A feedback queue is when your priority, for example, changes over time. Or you can move between queues. Maybe at some point this process was here, but maybe for some reason you have to move it up to here. So there is a feedback that should be, calculated in the OS to move processes within the queues. So the multi-level feedback queue scheduler defined by the following parameters. So you have multiple queues, and well, how many, right? In here, in the 4.4, it's like 64 queues. So all the way from 0 to 63. And then scheduler algorithms for each queue. So maybe you have, as I mentioned in the example, you have different algorithms for queue number 1 to queue number 48. And then method used to determine which queue a process will enter when that process needs a service, right? When a process is entered, is it in the this queue or this queue? Method used to determine when to upgrade a process or downgrade a process, right? These are how we should think of MLFQS. So this is an example. We're going to talk about these jargons next. Don't worry about them. But round robin is when you have just one thread after another, like a queue, normal queue. And first come first serve is obviously also clear. Whoever is scheduled first gets scheduled all the way till it's done, and then the next, right? So in the round robin, you go back to the list, and then again, it's a time based, right? Each thread gets some time. So this is a multi-level example. So when a thread gets created, it goes back. It goes to this queue. It is allocated some time within this queue. And if it's not done, that means maybe it has some long job to do. Then it goes back to this queue. Within this queue, they are allocated longer time, but again in the same round robin fashion, one after another, not to starve other processes or takes a lot of time from CPU. If it's still not done, maybe it's a huge process or something, then it goes to a first come first serve list. So every now and often CPU would just take one of these and then run it completely till it's completely done and then put it away, right? This is an example. So this is the 4.4 BSC priority-based scheduling. Again, in the scheduling lecture, we're going to talk about more in detail. So there are multiple queues. Each of them have multiple threads, and then the priority goes up. So as long as there is a priority, higher priority thread within this queue, none of these queues can happen or get scheduled. Within this priority, if there are multiple ones, they should have a round-robin time-based scheduling. And then there are ways how to calculate the priority over time. The priority changes based on how much CPU time a thread has been recently using. That if it's too much of a CPU you're using, maybe your priority should go down, not kill the CPU. And then how nice a thread is. This is again something that we talk about. So a nice value is basically how nice of a thread is to others. So if a thread decides that I want to be a little bit nicer to others, I'm not that important, I'm a gentleman or a lady, so you go ahead first. It's just like that. So they can decide that by themselves, right? Up to some level, they have a range. So this gets calculated or into the formula. if how many threads we have on the CPU. If it's like a couple of threads, maybe it's fine. But if you have too much, that's also a feedback, right? Maybe we should treat them, again, a little bit differently. So again, these things will be there. So these are last part of your project, so you don't have to worry about them now, but I put it in this because you have to probably come back to this slides later. We're going to cover the details in the next lectures, right? So these are the functions to implement in your thread.c: get nice, set priority, get priority, recent CPU, load average. These are all the things that you need to implement. And then this is the suggested of implementation, as I mentioned earlier. So alarm clock start with this. It's easier to implement compared to the other ones, and also easier to test. Then the priority scheduler, and then the donation after when you're done with the priority scheduler, and then the MLFQS. This is a little bit more difficult and, again, independent on the others, right? So use printfs and asserts and backtrace and GDB. These will be covered in your recitations. You'll need them. Definitely use them. How to run your Pintos under GDB. This is an example. But remember to pay attention. There are dashes, spaces, not spaces. These are all important. If you miss them, if you run something and it's not working, one of the reasons is that. Sometimes there is a space between dash, sometimes it's not. Pay attention to how it is in the slides or in the documents, right? And then becomes a testing. You make clean. If you run make check and make each test, this is 1 of 8. If you make grade, you get the result all over, right? So we're going to go over the grading in a couple of slides. You get the pass and fails of the make check. In the grading, when you call make grade, you're giving a %. So there are 93 points, but it's scaled to a %. This is what we care because each point is weighted, right? So these 18 they're just like a little bit weighted, especially in the other projects. The weights are different. So right now, whatever you have been given it gets like 40 points passed because it's like passing these tests, but with busy waiting. Remember, whenever you get a score, make sure that's not because of your busy waiting, because the busy waiting will lose that 14 points. Also, turning the interrupts on and off for synchronization purposes will lose you that 14 points, right? So this is not a part of your actual grade. This is just wrong. But when you get your grades, your grade will scale down from 100% to a 90%, and that's part of your source code. And then your design document is the 10% of your Project-1 grade. This is due on March 1st. This is due on 15th. Remember that? And again, whatever you get on your source code, it should make sure this is not the case for busy waiting or interrupts. And again, remember that this is the Friday night, and there is no late submission. Right now, I apologize in front of everyone to that group or groups that are having issues at the last minute. I'm so sorry, but hopefully I don't meet you. Basically, you won't exist because of this warning. But so remember to just do it early on because you get like unlimited submissions to AutoGrader. So submit it every now and often. There's no need to wait for the last minute for any issues, right? So just resubmit whenever you want. And the instructions will be posted on Piazza, all right? So post notes if there is any questions or issues or having any issue with your groups on Piazza. And if there's any questions, I'll be more than happy to take it.